Okay.
OH, then it's
Mouse, zip them. Lights are green, unless I give you a turn to talk. Okay, if I raise a hand, can someone identify one of the various labels on this equation for us just to remind us? So acid, base, conjugate, give us one of them. Evan, give us one.
HNO2 is an acid
And how do you know that?
because it's giving one of its hydrogens to H2O in the process.
Perfect, so definition of acids is they give up their H. Good, how's my base, Evan?
H2O is
Add to that, Allie.
H2O is the base because it's the one that like receives the H from the acid.
Good, so our definition of bases is they are acceptors of the hydrogen, they receive them, or the proton as it's moving. Good, how's my base? Add to that, Zach.
NO2 is the conjugate base
Good, and how do you know that?
because universal reaction with
Good, so he's looking at it, if you go in this direction, this substance is gonna receive the H, right? You can also look at it as it's the pair of the acid, right? It's the thing the acid turns into, becomes the conjugate. Good, someone else wanna add?
H3O is the conjugate acid.
Good, and how do you know that, Bryson?
Because it's the one receiving the H.
Good, right, so it's the one that received the H from the base. All right, there's one more label I want to add to this that we don't have. There we go, Ephraim. Are they strong or weak? Remember how to tell?
well, H2O is that a weak base.
Good, so we know that's like not as strong. Good.
We do have, I don't think that's strong, but I had
That's okay. How's my face, Ephraim? Zach?
HNO2 is a weak acid.
And how do you know that?
It's not on our list, but it's conveniently to the left.
Right, so there's 7 strong. If it's not one of those, by default it's weak. Anyone else, by raise a hand, have another way you can also know there's not strong ones? Person?
Well, if there's not H2 on the other side of the equation, then one of them has to be weak.
Good, so that's another way is like in a sense of, it doesn't tell you both, but if it doesn't make water into salt, then you know one of them at least has to be weak. So that can be another way of knowing. So awesome, thanks guys. Okay, we then ended, after we did a lot of labeling last time, okay, we then transitioned into the equations for calculating acids and bases. So scientists developed this thing known as the pH scale. Okay, we learned that pH is a measure of how much H plus, okay, side talking needs to stop, is how much H plus is floating around. If I could magic school bus into this hydrochloric acid, the pH would be a measure of how many H's are floating around in there. Like I could count them all up and that would be the pH. So the more H pluses you have, the lower the pH becomes because of how the log flips it. Okay? This is the inverse for finding H plus. I put a star because this one's not on your formula sheet. Okay? Once again, we did these last time. Okay? Now, this will be our new stuff we haven't filled in. So flip to the top of this page, which is page 6. And this should be the next blank thing, if I'm right.
Yes.
Yeah? Okay. All right. There's a box missing. There's supposed to be 3 boxes on that page. Mine has a box. Yours just has a space. Everyone see that? So in that space, write this equation right here. So in the space at the very top of the page, write this equation. There's also a way or a scale known as the pOH scale, which is the complete opposite of the pH scale. Meaning bases have low pHs and acids have high pHs on the pOH scale.
Huh.
Now, we don't really use the pOH scale as like a way to talk about acids and bases, but as you'll see here in a second, it's a helpful way to convert across, particularly with a base. Okay, and we'll get that to in a second. In this next box right here, write this equation. You can also take the pKw of Kw. Does anyone remember from last time what Kw is? Oh, I heard someone say the W word. Water. So it's the equilibrium constant for water. Do you remember its value? It's on your formula sheet, so you don't really have to, but it's 1 times 10 to the negative 14. Remember, it's the extent at which it actually breaks apart, which is very, very, very small. If you take the negative log of that number, you get 14, which is why the pH scale runs from 0 to 14. Okay, so the pH scale runs from 0 to 14. Then, in our final box here is the connection between our two scales, where if I have the pH of a solution, and I add it with the pOH of that solution, it will always equal 14, as long as we're at 25 degrees Celsius. Because once again, the pH scale gets shifted if you're not at 25 degrees, because of equilibriums.
What's that?
Like 78 maybe? Like room temperature-ish is what it's considered to be. Okay, let's try, we're now gonna practice putting all these equations into use, okay? So I'm gonna do some, and then we'll have you guys try some to practice it, okay? All right, so we have this data table here, and the goal is we want to fill in the missing pieces and then identify if each solution is an acid or a base, okay? So looking at our first one here, I have the H3O+, which remember, this is the same thing as H+, this is its nickname, this is its real name, right? But they're one and the same, okay? We have how much OH there is. It told us the pH, and then we need to find the pOH. First thing, let's look at what's given. From what's given, do I already know if this is an acid or a base?
No, Jazz.
I do. Now, there's two ways you can look at it. Acids have more of this than they do of that. So which one's bigger, 10 to the negative 3 or 10 to the negative 11? So since I have more of this, this is acidic solution. The other thing to remember is that pH, if it is less than 7, that makes it an acid. Remember, 7 is the middle, below 7 is acidic, above 7 is basic. All right, coming in to fill our missing piece here. So here's all the equations we could use. Oh, I guess I'll write the last one up here that we erased. There's different ways you can get to the same answer. I try to pick the one that just seems the easiest. So to find pOH, if I have pH, this equation is the best choice. Okay, so to find this, it would just be 14 minus 3, and so the pOH is 11. I'm just writing the equation in the box just to kind of remind you where they came from. All right, this one, deciding if it's acidic or basic, I'm going to look at the pH. Since the pH is less than 7, this is also an acidic solution. Now the missing piece here is the amount of H+ floating around. So in this case, we can take the negative log of the pH, because once again, here's my equation, that pH equals, oh wait, but we want to do it backwards. Sorry, I wrote that weird. Erase that. Hopefully you didn't use a pen. Because we want to find H+, and I know pH, so we're going to do 10 to the negative 2.28. And plug that into your, don't say this is your answer, by the way. Plug that into your calculator. And that gave me 0.0052. Questions on that one? Seeing how once again these equations are kind of linked. All right, C is missing a lot of information, but I can actually still say, is it an acid or is it a base? Yeah, so I actually can say it's a base because the pH is above 7. So now I need to fill in the missing pieces. So for this one, I'm going to do the same. So we're going to do 10 to the negative 9.28. And I got 5.2 times 10 to the negative 10. These, by the way, are molarity for the concentration ones. Now, this one I could find with what I have, but I'm going to move to this one because this one feels easier. because this one I can just do 14 minus my pH. Right, so 4.72. And so then, now that I have this, I can do 10 to the negative 4.72 to find my OH. Which 1.9 times 10 to the negative fifth. So it's kind of like a Sudoku type idea. You have a lot of equations, you have some pieces, use the equation that finds the missing hole for you. But any questions before I have you try some with your table buddies? Okay, I'll give you 5 minutes. You have 8 smiley faces up for grabs here, people. Okay, so smiley face for every blank and identifying if it's an acid or a base. Ready, set, go.
Oh yeah, it literally is just that. That's kind of funny. Oh, we need to keep OH. Did you get POH of 2.5?
Just 14 minus 2.5.
11.48.
Negative 11.
No, wait, we do 10.
What is it?
Wait, I think I had
No. If it's less than 7, it's an
Oh, I think about this one.
Oh, this last one.
Yeah, I
My
said-
bad, my bad. Yeah.
Yeah, I said use it.
I never noticed that. Oh, it's super because to get
Yeah, I think that's what we did.
and then I got
The polarity of the acid. You already get the acid.
So the polarity of OH of the base is 2.4 10 to the negative 13.8. And then the molarity of the acid
Awesome stuff. I wonder if you can use ratios like this over this equals this and then you use that. I'm gonna try to 13.
Yes, I can write it less here because I have a little bit more. We do have, I know from me.
So this needs to be converted.
yeah, did you
You can borrow mine right here. Alright, you got 1 more minute about, and then we'll check our answers. Don't forget, I also want to see labels of is it an acidic or basic solution?
Darn, I thought I had a good brain. Because the molecular was fun though.
How long are you in this?
2 weeks. Oh, you're probably totally right about that. Yeah. It's not linear, it's like, you're totally right.
Okay, give me a fist if you're ready. Give me a finger if you're like, I need just another minute. 1 more minute looks like. Okay, 1 last minute and then we'll check.
I couldn't figure out the time signature of what someone said.
I think it's 7-1.
Yes, I did. Someone last parent said they couldn't.
14.
Yeah.
Well, 3.5 2.
Yeah.
How many? That was 14, 6. Wait. Would that be 6? I said 6, 8. Sorry. Wait. No, yeah. Wait. 14, 8.
Okay, ideas up front. Let's go through and make sure we're on the right track. If you got it wrong and you don't understand why, let me know and I can walk through it. But I'm just going to go through the answers. Okay? Here's my answers. Okay, so D, you should have said is a basic solution. So I have a smiley face if you did that. Okay? The H3O plus, or the hydronium concentration, should be 1 times 10 to the negative 9. Questions on D? So that's a smiley face as well. Okay? Solution E is also a basic solution. Its hydrogen ion concentration should be 3.3 times 10 to the negative 12. Its pH is 11.48, and its pOH is 2.52. Any questions on solution E? Solution F, you should have said, is an acidic solution. It has a pH of 1.35. So I'm reading that in a weird order. I don't know why I did pH first. The hydronium concentration, which is H3O plus, should be 0.045. The OH concentration is 2.2 times 10 to the negative 13. All right, any questions on those calculations?
Oh, that's the jacket.
Questions right now? Okay. All right, take a look up here, everybody. Let me show you a little demonstration. So with the pH scale, we have a variety of ways in a lab setting that you can actually measure pH. Now, what is pH measuring?
How much hydrogen?
Good, you know, that's what it is. How much hydrogen is alone in the water? Okay, so if it's still bonded to something, that doesn't count for pH. It has to be an H all by itself. Okay, now we have things known as a pH meter, which you just, like a thermometer, you stick in and it'll straight up give you the number. Those are the most accurate way of determining what is the pH. We have some more fun visual ways of determining pH, and those are indicators. So indicators are substances that actually change color depending upon the amount of H plus floating around. Now the thing to not get deceived by is there are, I don't even know how many indicators in the world, and they can be a rainbow of colors for the same pH. Okay, so it's helpful, but you have to know what particular indicator am I working with, because that changes what it does. Okay, so for example, right here, I have so this is some sodium hydroxide, so it's a base. Okay, I'm going to add it here to this beaker. Okay, so notice same substance in both these beakers. Okay, then I'm going to add some indicator to this one here.
Whoa.
Ooh, don't spill. Okay, then I'm going to add some indicator to this other one here. Oh, down's empty. Hold on. The bottles are drying out. Okay, take 2. Okay. So is this the same substance as the other one? With the indicator, do they look like the same substance?
No.
No. Right, so indicators can be deceiving in the sense of this one is blue at that pH, this one is purple at that pH. Okay? Indicators also have a flipping point. So that's what this graph here is showing you the flipping point of where the color change happens. So for example, with methyl violet, anything below a pH of about 1 is going to be yellow. But everything above 1, so 2 through 14, is purple. So it's not really helpful in terms of outside of where the flip happens, but sometimes you want to see that flip, and we'll talk about it on a particular day. Now there are other indicators that do a range of colors. We have the one that's the favorite of, it's called the universal indicator. So this indicator I'll show you in 3 different substances. So we'll get our base again. So I'm going to put base in this one. I'm going to put water in the second one. And it won't be perfect because I'm not using distilled, but we'll just go with what we have here. Okay, and then I'm going to put an acid in the third. So hydrochloric, oh, there's still somebody here. So now, 3 different substances, and I'm going to show you the same indicator in each.
All different volumes.
They're different volumes.
Matter.
We'll talk about that actually in a second, but good observation. Okay. Okay, so this is my acid. This is my water. And then this is my base. So the universal indicator actually does the whole spectrum of the rainbow for all pHs. So it is a little more helpful, but it still doesn't tell you the fine details of 14 point what or 1 point what. And then you also have to use your eyes to gauge of like, oh, is it slightly red-orange or is it just red? But it still can give you an idea in terms of, this one is helpful in terms of, okay, I know this is an acid, I know this is a base, and this one's fairly neutral. Okay? So indicators are fun and they're helpful, but also be cautious with what they're telling you straight up. Yeah, Ali.
Just like out of curiosity, what are indicators like usually like what chemicals are like?
That's a good question. And I don't know how to answer it. This has been something, indicators are crazy. And to be honest, in all my studying of it, they still kind of feel magic. Because like, it's just, there's a chemical, the indicator is a chemical itself. And that chemical, depending on the amount of H's in there, can change colors, which is crazy. That's the only answer I have. So sorry. Yeah, so pH strips work the same idea, where the indicator's just like, I don't know that word, just like painted onto the strip. But same concept, yeah. So, okay, we're gonna do a little thing here before we jump into our next topic, to make sure we have a good visual of it. Okay, I forgot to print them out, but I'm going to next because I think it would help. I want you to imagine there's a beaker right here in the middle of your table. Can everyone use your imagination? Okay, there's a beaker here. Okay, so when I say hands off the beaker, that means you're not touching the middle. Okay, all right, everybody, I'd like to take your acid and pour it in the beaker, aka your Legos. Okay, pour your acid in the beaker. Don't change what it looks like though. Don't start making dogs and things again. Just pour the acid in the beaker.
No, I'm gonna touch the burn yourself, guys.
Okay, pour the acid into the beaker.
We're wearing acid.
To some extent, I don't know if latex can resist like the highest polarity. I've never liked it. I love taking it before. That's what happens when you pour it on your toast. Okay, everyone have their acid in their beaker? All the acid, the whole bag, dump it all out. Not the base though, leave the base in. Okay, we talked about last time, so we have two classifications of acid. We have strong acids and we have weak acids. Okay, by definition, the difference between a strong and weak acid is the amount that it breaks apart. Strong acids are considered strong electrolytes because they break apart entirely. Meaning, for every one of these, so let me clarify this by the way. So this is your acid. The small Lego, everybody, that's your H. The big Lego is the other half of whatever acid we're dealing with. There's HCl, right? This would be H, the black would be Cl. If it was acetic acid, then this would be the H, this would be C2H3O2. That's the other half of it. Everyone visualizing what this represents? Okay? When acids are strong, they all exist like this in the beaker. So I want you to turn your acid into a strong acid. Ready, go. Turn your acid into a strong acid. Have a smiley face. Good job. Have a smiley face. Good job. Have a smiley face. Smiley face.
I love smiley face.
Have a smiley face. I know. We don't need it. Have a smiley face.
Sounds very yummy to me.
We're using it in our beaker. In the beaker. Okay, we're not using the base, by the way, so keep the base in the bag so you don't mix up the pieces. Okay, so right now, you're looking at, everyone look at it. We've magic school bus. This is my magic school bus. We're zoomed in. This is what you would see inside this beaker. You would see a bunch of H's floating around, and you see a bunch of L's, CL's floating around. Now, what is not being shown in our model that's here? Water, right? There's also always water in acids and bases. They're aqueous solutions. We're not going to model them because there's 5 zillion of them. Okay, but the water does play an important role. That's why the H, we nickname it this, but what does it actually become with water? H3O plus, right? So this always bonds with water, but really, once again, it's H. So if I wanted to calculate the pH of my solution, what would I be counting? How many hydrogens in the volume I'm given, okay? Okay, now we're going to transition our flask, our beaker, to a weak acid. The difference between a strong acid and a weak acid is weak acids do not have 100% dissociation. So turn yours into a weak acid of your choice. Ready, go.
So some of them
done?
Winner is us.
Is that a weak acid?
I agree.
Have a smiley face.
Yeah, that's not smart.
Okay, have a smiley face. Have a smiley face. Have a smiley face.
You're the perfect type of person to get.
Okay. Have a smiley face. Good, have a smiley face. Have a smiley face. Okay, did I check? Oh wait, where's our pyramid people? Okay, have a smiley. Good job. Okay, now. Oh, did I not check you? I don't like that. Fix that. Have a smiley face. That's not what they would do.
Hey, the assholes just want to chill.
Okay, now here's my question for you for your next smiley face. You ready? Talk as a group. Leave your ass alone. Stop touching the acid. Put it back. Put it back in the beaker. Stop building things. Legos are just too chunky for some reason. Okay, true or false? Here's the question I want you to answer as a group, and then we'll all respond at the same time. Okay, true or false? A strong acid will always have a lower pH than a weak acid. True or false? Talk as a group and come up with your answer. Ready? A strong acid will always have a lower pH than a weak acid.
Well, yeah, because it's the same amount of That's boring.
Would it help more because they have labels and then when you tend to build dogs? I haven't made my other half. So instead of those, if there's just two different colors that you would like in a sense show like houses together.
Yeah, with the clear label.
I kind of wonder too if the labels would help your brain. You don't have to process as much. Legos are easier. Okay, we're gonna respond in 5 seconds. So what you're gonna do is if you think the answer is true, you're gonna make a T when I count down to 5. If you think the answer is false, you'll make an. Okay, this is sign language, this is not. But it's just people remember. Okay, ready? In 5, 4, 3,
True or false?
2, 1, it is false, 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 false. Oh, true, false, false. Okay. Is their table willing to justify their answer for a bonus point, please? Go ahead, Bryson.
So our table discussed is if you have the same like molarity and like volume of a substance, then it's the same amount of hydrogens between the two, no matter if they're broken off or weak or strong. So that's why we said false.
Good. So the other thing, so it is false. Have a smiley face for that. The other thing we have to consider is molarity. For example, what is pH measuring again?
The amount of hydrogens.
Right? The amount of this. If I have the same Lego blocks, then yes, a strong acid's going to have more of these floating around than a weak one. But if I have 1,000 Lego blocks of my weak acid, even though only some of them break down, there could be more of these floating around than a strong acid of a low molarity. Okay, here's 2 flasks to prove it to you. This right here is a point. Sorry, they're not labeled what they were. I just used the ones from last time. This one is a 6 molar weak acid. So very, very high concentration, but it's weak, meaning it looks like that, right? Some of them are broken down, some are not. Okay, this is a 0.01 molar strong acid. So notice, pH-wise, they're pretty similar. I'd even argue that the weak one looks more red to me and this one looks even more orange, right? But you can have the same pH, but one be strong and weak because concentration plays a big role. Does that make sense? Questions on that idea? Yeah, Alex.
So you wouldn't be basing pH off of any of these where the H is still connected. It's only the free floating H.
Great question. Yes. So pH is only measured of the free floating H's. Yeah. Yeah, Lily. Did you have a question? Okay. Yeah, Ali.
So then, does that mean if you increase the volume or like the concentration in a sense, then the color will change to actually indicators?
Say it one more time.
So like, if you add more volume, then will, I could say like the pH or the color will change if you add more volume because it's increasing.
The volume won't, because since it's a measure of molarity is moles per liter, so more of it's just going to be more of the same color. But if you can just add more moles of it, then the concentration would go up. Does that make sense? Okay, all right, put your acid in the beaker and don't touch it. Oh, actually, change it back to a strong acid for me. Change your acid to a strong acid and then hands off. And let's look at a problem here. Wait, I gotta remember to pass back your FRQ. When are we done today? 15. Okay, we're okay. Stop me at like 11:10, or maybe like 11:08.
I agree with that.
Right.
Set a timer for 11:11. I have a worse of time, Pete. Someone help me.
Okay, so as we just said, as what's on your table, strong acids and strong bases are strong electrolytes because they break apart completely in solution. So our next step in our journey of calculating pH is calculating pH of an actual substance. The problem we did before just were like, oh, solution A, solution B, we didn't know what they were, and we just knew the actual amounts. Now it's a matter of, okay, I have this acid, I have its concentration, what is the pH of that? How is that calculated? Okay, so first thing, it's going to be the phrase of the unit. What is pH measuring? Good, so pH is how much hydrogen is floating around. So if a problem says, what is pH? Once again, this is the idea of where I ask questions to the question. Right? The question tells me, it says, what is the pH of the solution? My brain says, okay, well, what is pH? Well, pH is a measure of how much H plus there is. So I need to know how much of this there is floating around, because then that can be plugged into here to get me pH. Okay? Now we're going to set up a Rice chart so we can see how much there is. If you thought they were going away, they're not.
I say we roll.
Okay? Set up your Rice chart. Okay, so initially, all right, eyes up front, lights are green, side talk, stop. Initially, I know the concentration is 0.04. So I'm going to put that in here as my initial amount. Now, just to clarify, technically we don't normally put molarity in here, but as long as the volume isn't changing, or sorry, the liters aren't changing, then we can just use the molarity as the moles. Which in this case, we're not pouring liquids in, it's just a set substance. What would these be initially? 0. Good, right? Because it hasn't happened yet. Now, since this is a strong acid, how much of that is going to be left in the end?
0.
It's all going away. Look at your table, right? There's none of it that is still together. So this is going to decrease by all of it, which means this will increase by, good, the same amount because of the ratio. Now I can take this and take the negative log of it to find my pH. Okay, so just do the negative log of 0.04. yet?
1.40, sorry.
1.40. Which, is that a logical pH for an acid? Yeah, it's good to do a quick check. Because if you got a pH of 9 and it's an acid, you might want to type something back in your calculator.
Or redo the problem.
Questions so far on that one?
Just give up on the test.
Okay, let's take a look at one that's now a base. So in this case, sodium hydroxide is a base, not an acid. So we're still trying to find pH. When it's a base, the logic can be the same, there's just a little bit of flip you have to do at the end because the H plus isn't directly there. So that's how I know it's a base, is because it's making OH, it's not making H plus. Remember, all our strong bases have OH attached to them. But, as we learned before, if I can find my OH and POH, we can get it back to pH. So same idea, we're just going to start by getting to POH first, to then get to the pH. Okay? So, set up my rice chart here. I'm starting with a concentration of 0.028 for my sodium hydroxide. This would be 0. What's the change going to be? All of it's going away, because that's what strong bases do. 0.028. So now I can do the POH is equal to the negative log of the OH concentration. Somebody type that in yet?
1.55.
Thank you. But I don't want to circle that,
No.
because the problem wants to know my pH value. And so then I can just do 14 minus to get to my pH. Was that 12.45?
12.45.
Which, is that a logical pH for a base?
That's correct.
Yes.
Yeah. Yeah, Alex.
What does the P mean in pH?
It stems from an idea of like, I looked it up last year, and it's like power of, because of how a log function works, is where it comes from. But, yeah. That's why like in all of these like pH, pKW, it's all just the negative log of that thing. Like when you say pH, you're taking the negative log of that thing. When you say pK, you're taking the negative log of K. So if I was going to take the negative log of Bryson, then I'd say the P of Bryson.
Wonderful.
That makes sense.
Okay, try this one with your table for a quick smiley face.
Oh yeah, because it'll dissociate. Yeah.
Negative log of 1 is 0.
Why? Why do you think it won't work?
Oh, it's like that acidic. Like it's really that acidic.
You would die if you touched it.
Yep. We will still use a rice chart, but we're going to need other information to help us know how much is going down because it's not going
I need to
down.
review
Yeah, good question. You just stole my pink pear share.
Oh, so sorry.
No, I'm glad you were thinking about it already.
It's base 10. Remember?
Right, well, because this is the power.
But if you do a negative log, so 0 is equal to log power of 10. Hey, Alex. So we have to get rid of the negative, right? So you know 0 is equal to log of 1 to the power of 10. Power of 0, 1 is equal to.
I guess I just need to widen my
Because log is just power of 10. The log of
Okay, show me on your hands what you get for your answer. You got 0. Have a smiley face. Any questions? I walked around and saw that on most people's papers, but any questions on it? Now, is a rice chart really necessary with these 3 problems? What are you taking the negative log of?
The molarity.
Yeah, just the molarity of it. So you don't have to write out rice charts when there's strong acid or strong base. I did it because hopefully, once again, to help you understand why we're just taking the negative log of it. Okay? All right, last thing that I want you to do is on your own, I don't want you to talk to your neighbor because I want your own thoughts. I want you to answer that box at the bottom. Okay, so on your own, no talking. Okay? On your own, no talking. Zip the lips. Tell me your thoughts on that last question. So we just found the pH of strong acids and strong bases. But finding it for a weak acid is not as straightforward. Why do you think that is? When you're done, if you could return your acid to their original orientations and put them back in the bag for me.
I'm sure this camera has seen both Bryson and my hair throughout this time. Like, looks like looking back or something. Oh, yeah.
This is Althea's time.